Hello everyone, my name is Tian. Today I would like to share our paper called Cluster-Based 3D Keypoint Detection for Category-Agnostic 60-pose Tracking. 60-pose includes 3D translation and 3D rotation, totally 6 degrees of freedom. Tracking means recursively estimate the change in pose over time t. 6-pose tracking can be performed at instance level, where CAD models are known. 60-pose tracking also can be performed at the category level. Those methods will train a model for one category. Additionally, 60-pose tracking can be performed at category-agnostic, which means the model can track the object regardless of the category information. We selected 4 related works. The first 2 methods named SE3 TrackNet and post-RBPF. They use 3D models to achieve instance-level 60-pose tracking. But the problem is CAD models are limited. It's hard to extend to other instances. Recently, 6-pack does not require 3D model and achieves category-level 60-pose tracking. But the problem is it requires prior knowledge of the category information. More recently, BundleTrack achieves category-agnostic 60-pose tracking, but it directly using existing keypoint detector with fixed pretrained parameters. We proposed a cluster-based keypoint detector for category-agnostic 60-pose tracking. The framework includes 3 modules, and the whole pipeline is in an end-to-end manner. We use RGB, target mask, and depth as input, and the output is protected keypoints. We can use the same framework to obtain the keypoints from the previous frame and the current frame at the same time. Then, the 60 pose can be recovered by using least square optimization. We use target mask, depth, and camera intrinsic to obtain target point cloud. Then, we use Open3D to remove outlier in the point cloud. Following, we use PointNet to obtain geometric feature. At the same time, we use RasterNet to obtain appearance feature from curved RGB. After that, we use encoder to fuse appearance and geometry feature and obtain fused feature map. The feature map contains points XYZ coordinates and features. The points XYZ coordinates are indexed to their corresponding features. In order to make full use of the local information of the target object, we use the split module to separate the target object into different clusters and protect key points from clusters. To achieve the split module, we first need to sample some initial points from the point cloud and find nearest neighbors for each initial point and group them into a cluster. As a result, we can split the object into several clusters, and each cluster contains local feature of the object. After that, we use keypoint detection module to detect key points. This module includes 3 perception layers and 2 fully connected layers. We use this module to detect 1 key point from each cluster. As a result, we can obtain n key points. Now, let's talk about the loss. We have 4 loss functions. The first one called central loss, which encourages the protected key points are close to the cluster center. It can make sure the protected key points are eventually distributed on target object and easy to track. The second loss is silhouette loss, which makes sure the protected key points are in the silhouette of the object. The third loss named mounted view consistency loss, which makes sure the protected key points from 2 frames are from the same locations. The last one named pose loss, which directly compares the ground truth pose with protected pose. We visualized the cluster results and the 60 pose results. The first row displays cluster results over time. As we can see, the cluster in consequent frames matched well without prior category information. It helps us achieve category-agnostic 60-pose tracking. The second row shows the corresponding 60-pose result, which is visualized as a 3D bounding box. For quantity result comparison, we use 4 measures. The first one is orientation error in degrees. The second one is translation error in centimeters. The third one is 5 degree and 5 centimeters, which calculates the percentage of orientation error smaller than 5 degree and translation error smaller than 5 centimeters. The last one is IOU25, which calculates the percentage of overlapping between ground truth 3D bounding box and protect 3D bounding box is larger than 25%. As we can see the results in the table, our AGN outperforms most cases and achieves good tracking performance. The 6-pack SPE has a marginally better performance than our AGN. However, 6-pack SPE is a category model that trains one model for one category. However, ours AGN trains one model to track the object regardless of their categories. For fair comparison, we train our pipeline on 3 unsymmetrical categories as ours ASY, and also train the 6-pack in same setting as 6-pack ASY. As we can see, our results surpassed the 6-pack ASY. We achieved unsupervised keypoint detection for category-agnostic 60-pose tracking. Corresponding clusters help us find matched keypoints. In the future, we will investigate pose tracking under heavy occlusions and add post-processing to refine protect pose. For more results, please scan our QR code. Thank you very much.